Hello friends, I am back for the third part of the lecture upon solid state. So in solid state part 1, we discussed the basic difference between crystalline solid and amorphous solid. We discussed what is a space lattice, what is a unit cell. Then in the second part of the lecture, we discussed the number of units per unit cell. Then we discussed the relationship between the radius of an atom and the edge length. We also discussed the packing fraction or packing efficiency in simple cubic unit cell, BCC unit cell, and FCC unit cell. So today we will be discussing the part 3 of the lecture upon solid state. So in this lecture, I will be delivering a lecture upon close packing and what are the different types of close packing, etc. So let us go to my PowerPoint presentation. So this is the PowerPoint presentation. So it is solid state part 3. Myself, Vedanta Kumar Bora, Associate Professor, Department of Chemistry, DR College, Gulaghat. You can contact me in my email. It is vedanta69@gmail.com. So today's topic is close packing of sphere. So already we have assumed that atoms are spherical in shape. They are hard spheres. They can bounce to one another, etc. So now I will give you two diagrams. So in close packing, what happens? The units, that is the atoms, are close to another so that each atom is surrounded by maximum number of atoms. So in any close packing arrangement, you will find that each atom is surrounded by 12 other atoms. Of these 12 atoms, 6 atoms will be in the same plane, 3 atoms will be above it, and 3 atoms will be below it. So the number of nearest neighbor of an atom in a crystal is called its coordination number. So in close packing, coordination number of atom will be 12, and in close packing, each atom is surrounded by maximum number of atoms. So here I am showing you two figures. The figure on the left hand side, here you can see this is one line of sphere, or I can say one line of atom, and the second line of atom is exactly above the first line of atom, or we can say this is the first layer of atom. The second layer of atom is exactly at the top of the first layer of atom. So this atom is exactly above this atom. Then the third layer of atom is exactly over the second layer of atom. So if you say that the geometrical arrangement of first layer is A, then geometrical arrangement of second layer is also A, geometrical arrangement of third layer is also A, and geometrical arrangement of fourth layer is also A. So we can call it as A type packing. So here these are the voids, these are the empty spaces. Now let us go to the figure of the right hand side. Here what you observe, this is the first layer of atoms, and the second layer of atom is not at the top of the first layer. So these are the atoms of the second layer. This atom is not at the top of either this atom or this atom. This atom is not at the top of either this atom or this atom. So the second layer of atom is sitting in the voids or in the holes of the first layer. So the geometrical arrangement of the first layer and geometrical arrangement of the second layer are different. So if I say the geometrical arrangement of first layer is A, the geometrical arrangement of second layer is B. Then the third layer, you can see it is exactly at the top of the first layer. So the third layer is exactly at the top of the first layer. So this is an atom in the third layer, and this is an atom in the first layer, and this atom in the third layer is exactly at the top of the atom of the first layer. So the geometrical arrangement of the third layer is A. So AA are similar. Then the fourth layer, you can see, fourth layer is not above the atoms of third layer. The fourth layer is the atoms is exactly at the top of the second layer. So this atom is at the top of this atom. This atom is at the top of this atom. This atom is at the top of this atom. So this arrangement can be called as AB, AB, AB type. And here you can see the vacant spaces is much less than the vacant spaces in this type of packing. So of these two type of arrangement, we call this is a close packing. Here you see that this is one atom and it is surrounded by 1, 2, 3, 4, 5, 6 atoms in the same layer. So in close packing, the maximum available space is occupied and there will be less vacant spaces or there will be less void volume. So if you compare these two type of arrangement, here it is the AAAA type, here it is ABAB type. The vacant spaces in the AAA type is much more than the vacant spaces in the AB type. So this type of arrangement represent a close packing. Now here you see there are two types of close packing. Actually there are three types, so we'll be discussing only these two type of close packing. Now you carefully look at these two layer close packing. Here the green balls, it represent the first layer, and the second layer is in the holes of the first layer, something like this. So suppose this is the first layer. The second layer of atom will not sit over this atom, but they will sit in the holes and not whole holes. It will be in the alternate holes. So one unit will atom will sit here, so it will occupy something like this. The other atom cannot occupy this hole, it will occupy this hole. Then the other atom will not occupy this hole, it will occupy this hole. So the second layer is over the holes, alternate holes of the first layer. So from sideways it will look like this. From the sideways it will look like this. So this is a side view of the arrangement. So this is the first layer. The second layer is sitting in the holes of the first layer. So second layer is not at the top of the first layer. Now we have the third layer, again a green layer, because this layer is exactly at the top of the first layer. Then again this blue layer, its geometrical arrangement is not like the green layer because these atoms are not above the green atoms. So here what you observe, that in this type of arrangement we get similar layers repeated alternately. So this is one layer, this is one layer, they are similar. This layer is similar to this layer, and in between these two similar layers we are having a different layer. So we can call this arrangement as AB, 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 AB type. And this type of packing is called hexagonal closed packing. So in hexagonal closed packing, the second layer sits over the holes in the first layer, and the third layer sits over the holes of the second layer, but they are not, and they are exactly above the first layer. And this way the different layers go on forming. So we get one similar layer, then a different layer, then another similar layer, then a different layer. So we call this type of arrangement as AB, AB, AB type. I think it is clear. Now look at this arrangement. You can clearly see from here. you can clearly see from here. What you can see from here, here again, this is the first layer. The second layer is sitting in the holes of the first layer. Then this is the third layer. Here what you observe, the atoms of the third layer is not above the atoms of the first layer. In hexagonal close packing, the atom of the third layer is exactly at the top of the atom of the first layer. But here, this is the third layer. That is, we are having white balls, blue ball and green ball. So the blue balls are sitting in the holes of the green ball and the white balls are sitting in the holes of blue ball, but these white balls are not exactly at the top of the green ball. So this layer we can call it as A, this layer we can call it as B, and this layer we can call it as C. Then the fourth layer, it will be similar to the first layer. So this type of arrangement can be called ABC, ABC, ABC type, which means similar layers will be repeated after two different layers. And this type of packing, closed packing, it is called cubic closed packing. It is called cubic closed packing. And here I am writing FCC, which means that cubic closed packing will provide FCC unit cell. And hexagonal closed packing, it will give rise to hexagonal unit cell. So closed packing may be of two types. So in closed packing, the maximum available space is occupied. So in closed packing, the second layer is not exactly at the top of the first layer. In fact, the second layer is in the holes of the first layer. So this is the first layer. These are the holes of the first layer, and the second layer is exactly at the top of the in the holes of the first layer. So the atoms of the second layer is not above the atoms of the first layer, which is similar, which is happening in both hexagonal closed packing and in cubic closed packing. In hexagonal closed packing, what you are having, the third layer, it is sitting in the holes of the second layer, and the second layer is exactly at the top of the first layer. So we call this arrangement as AB, AB, AB type. And in cubic closed packing, the second layer is not at the top of the first layer, and third layer is also not at the top of the first layer, but the fourth layer is exactly at the top of the first layer. So we get similar layer repeated after two layers. So green layer, blue layer, white layer, then again green layer. So if you start from blue layer, we have the white layer, we have the green layer, again a blue layer. So this layer is exactly at the top of the second layer. So this type of arrangement is called ABC, 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 ABC type. So hexagonal closed packing, it will give hexagonal unit cell, and cubic closed packing, it will give FCC unit cell. So here some rings are used to show AB and ABC type of packing. So here the black ring represents layer A. So these are the black rings. Then the blue rings, it is the second layer which is sitting over the holes of the first layer. So this is the hole of the first layer, and this is the blue ring which is the second layer, and it is sitting in this hole. So all holes of the black layer are not occupied, only the alternate holes are occupied. Then the third layer A, it is again sitting in the holes of the blue layer, and the third layer is exactly at the top of the first layer. So here you are having both blue color and yellow color. So this is an AB type packing, and it will give rise to hexagonal close packing. Then ABC type of close packing, it is also called cubic close packing. So here you are having this A layer, it is the layer at the bottom, and over A you are having the B layers. So the atoms of the B layer, these are the circles, blue circles, they represent the blue atom. Black circle represent black atom, and these blue atoms are not above the black atom. Then the third layer, that is the C layer, it is represented by yellow circles, and you can see these yellow circles, they are not exactly at the top of A, or they are not exactly at the top of B. That means A, B, C, they are three different types of layer. Here A, B are two different types of layer, and again the third layer will be similar. So if you are having a hexagonal close packing, you will get a hexagonal unit cell, and if you are having a cubic close packing is also known as ABC type, then you will get FCC units. So this is a FCC unit cell. These are the units 1, 2, 3, 4. These are the units at the four corners. This is an unit at the center of the face. Again, this is an unit at the corner, 1, 2, 3, 4, and this unit is at the center of the face. So cubic close packing will provide you FCC unit cell, and hexagonal close packing will provide you hexagonal unit cell. So your close packing, there are two types of close packing. One is a hexagonal close packing, which is also called AB type, and in this type you are getting similar layer alternately. And the cubic close packing is also called ABC type of packing, and here you get similar layer repeated alternately after two layers. And cubic close packing will give you rise to FCC unit cell. So here this is a close packing. This is one layer of close packing. This is your hexagonal close packing. This is the first layer. This is the second layer. First layer is exactly at the top of the second layer, and this is the fourth layer exactly at the top of the second layer. So you can call AB type. This is your cubic close packing. This is the first layer, second layer, third layer. Neither second layer nor third layer is exactly above the first layer, but the fourth layer is exactly above the first layer. So we can call it as A, B, C, then again A type of packing. So in either these two close packing, hexagonal close packing or cubic close packing, the volume occupied is 74%. 74% volume is occupied. That is the maximum volume that can be occupied by spheres, because here we are considering atoms to be sphere. So this is a side view of hexagonal close packing and your cubic close packing. So cubic close packing is also called FCC because it gives face-centered cubic unit cell. Here, this is the first layer, this is the second layer, this is the third layer, that is AB type. So this is the A layer, B layer, again A layer. So this layer and this layer are geometrically same. They are exactly, one is above the other. B layer is different. So this is your cubic close packing. This is A layer, B layer, C layer. We are using different types of color. A layer is not similar to B layer, nor B layer is similar to C layer. But again, the fourth layer will be similar to the first layer. So if you remove this one by one, here you can see this is one unit. This is one unit, and this unit is surrounded by 1, 2, 3, 4, 5, 6. So this particular atom it is surrounded by 6 atoms in the same plane, and 3 atoms above it and 3 atoms below it. So this atom will have 12 nearest neighbor, and the number of nearest neighbor is called coordination number. So in hexagonal close packing, the coordination number is 12. That means each atom is surrounded by 12 atoms. 6 atoms will be in the same layer, 3 atoms will be above it, and 3 atoms will be below it. So the coordination number will be 12. So similarly in cubic close packing, the layers look same, but geometrical arrangement is little bit different. But still this is one unit, and it is surrounded by 6 units like hexagonal close packing. So in the same layer it has 6 nearest neighbor, and above it there will be 3 neighbor, below it there will be 3 neighbor. So this unit will have 12 neighbor. That means its coordination number is 12. So here you can see this unit, it is surrounded by 6 units in the same layer, 1, 2, 3, 4, and there will be 2 atoms behind these 2 atoms, 6, and 6 atoms and 3 atoms will be above it touching it, and 3 atoms will be below it touching it. So this atom has 12 neighbors, and we call its coordination number 12. So both in hexagonal close packing and in cubic close packing, coordination number is 12. Now this is a body centered cubic unit cell. In body centered cubic unit cell, we do not consider it as close packing because only 68% volume is occupied. In the other class we have calculated it. The packing efficiency of BCC unit cell is 68%. And here the coordination number is 8. So this is one atom, and its nearest neighbor are 1, 2, 3, 4. 4 above it and 4 below it. So its coordination number is 8. Then this is a simple cubic unit cell. Units are only at the corners. So here only 52.4% volume is occupied. And so we cannot consider it as close packing. So close packing is only hexagonal close packing and cubic close packing, where maximum volume is occupied, that is 74%. In BCC unit cell, 68% volume is occupied. In simple cubic unit cell, 52.4% volume is occupied. In hexagonal close packing or in cubic close packing, the coordination number is 12, and in BCC unit cell, the coordination number is 8, and in simple cubic unit cell, the coordination number is 6. So these are the summary: primitive, body centered, hexagonal, cubic. So highest coordination number is for hexagonal close packing and cubic close packing. And in both this case, the packing fraction is 74%. Here it is 68%. Here it is 52.4%. So this is an AAAA type. This is ABAB type. This is also ABAB type. This is ABC type. Now we will be studying what is a hole. Here you see these are the 3 units. These are 3 atoms. These are 3 spheres. And you can also form them in your home. You take 3 marble balls and you place the 3 marble balls in one plane touching each other. Then you will find that their center are occupying the 3 corners of an equilateral triangle. And in between these 3 units, there will be an open space which is called a hole. And in this case, the hole is called a trigonal hole. Why it is called trigonal hole? Because this hole is formed in between 3 atoms occupying the 3 position of an equilateral triangle. So similar to trigonal hole, we have tetrahedral hole. In tetrahedral, there are 4 atoms, 1, 2, 3, 4. 4 atoms occupying the 4 vertices of a regular tetrahedron. So out of these three vertices, 1, 2, 3, they are in the same plane like a trigonal. They are at the three corners of an equilateral triangle, and one unit will be above the whole of this tree. So in between these four units, there will be a hole, there will be a vacant region, and that is called your tetrahedral hole. So similar to tetrahedral hole, you may have octahedral hole. So in octahedral, there are 6 corners. So 4 corners will be in the same plane, occupying the 4 corners of a square, and one unit will be at the top and another unit at the bottom. So in between these 6 units, at the 6 corners of an octahedral, there will be an octahedral hole, which is called octahedral. Now from this it is clear that this tetrahedral hole will be the smallest and this octahedral hole will be the largest. So this is an octahedral hole. It is the largest one. So if an atom is placed in the octahedral hole, then its coordination number will be 6. And similarly, if an atom is placed in the trigonal hole, it will be surrounded by 3 atoms. So its coordination number will be 3. And if an atom is placed in the tetrahedral hole, somewhere here, it will be surrounded by 4 atoms. So its coordination number will be 4. So holes are the vacant space between atoms. Hole may be a trigonal hole, it may be a tetrahedral hole, or it may be a octahedral hole. Trigonal hole is formed between 3 atoms at the 3 corners of an equilateral triangle. Tetrahedral hole is formed by 4 atoms at the 4 corners of a regular tetrahedral, and octahedral hole is formed in between 6 atoms which are at the 6 corners of a regular octahedral. Now if you have a crystal which there are n atoms, suppose you have a crystal and that crystal contains n atoms in close packing, then there will be n number of octahedral holes. That means if you have a crystal having 100 units, then there will be n number of octahedral holes. So this is an FCC unit cell. These green balls, they form an FCC unit cell. They're at the corners of the unit as well as at the center. And the octahedral holes will be at the center. So this is an octahedral hole, and the octahedral holes will be also present at the edges. So this is an octahedral hole, and the size of octahedral hole is 0.414 r, where r is the radius. And for a crystal having n number of tetrahedral hole, for an n number of tetrahedral hole, there will be 4n number of tetrahedral hole. So the radius of a tetrahedral hole will be, okay, for a close packed crystal structure of n atom, there will be 2n number of tetrahedral hole. That means the number of tetrahedral hole is twice the number of the octahedral hole. So for a crystal with n atoms, there are n octahedral hole, and for a crystal of n atom, there will be twice n number of tetrahedral hole, and the radius of a tetrahedral hole will be 0.225 r, where r represents the radius of an atom. So today we have discussed what is a close packing. Then we have discussed what are different types of hole. We have discussed trigonal hole. We have discussed tetrahedral hole. We have discussed octahedral hole. And what you find that for an n atomic crystal, there will be n number of octahedral hole, and there will be 4n number of tetrahedral. So today we will be stopping here, and in the next lecture, that will be the part 4, I will be discussing ionic crystal. Until then, goodbye. Have a nice day. Thank you.